in this particular video, we're going to define what Hilbert spaces are, and why they're so interesting to model our quantum physics world, in particular, how we can use them to model the quantum physics states, very key subject. So let's go. In order to find a right model, that would be isomorphic to our physical world, one of the first steps that we need to take is to model the quantum states of the physical world. That means that we want to find elements in the mathematical world that would be isomorphic to the physical world quantum states. Now, to be isomorphic to the physical world quantum states, we want the mathematical world state to be, isomorphic and therefore have the same characteristics, like, contain a bunch of characteristic elements which would correspond to the properties, the physical properties in the physical world. We also want the states to be measurable and comparable to other states so that it's possible to express differences in, and we'll see why it's important, in particular to solve some of the quantum physics mysteries. And also, finally, we want them to be unitary, and we'll also use that in another mystery resolution. Now, the first two properties here, are easy to fulfill. Vectors, contain a bunch of characteristics elements, and you can add them and multiply them by numbers. So, that's easy to do. One thing which is a bit more tricky is to measure things. And for that, we want to determine how different two states are. And we will need a three-step process for that. The first thing is to define an inner product. We'll see in more details what that means in the few minutes. But basically, you have to add a certain operation which will take as an input two vectors and will output a number, that will characterize a given property. Here, it will characterize the amount of difference between two states. And the inner product is a very good tool for that. And it will also allow us to define a measuring operation. That's called the norm, is when you apply an inner product to the same vectors. And finally, we'll define a distance from that norm. So let's take an example here with the Euclidean distance, which is one of the easiest types of inner products. Actually, it's called a dot product in that case. While here, the measured distance in two vectors A and B will be equal to the norm of the difference here. In other words, the length of this vector here. And note that in particular, when two vectors have the same amplitude, the same norm, the dot product will depend only on the angle in that case, Now, let's keep that in mind. Now, let's look a bit closer to a simple example of Hilbert space, the Euclidean space. It's a good old space we know that we'll simply call space here. It's a vector space equipped with a scalar product. And how do you call a vector space with a scalar product or with an inner product? Well, it's a Hilbert space, as we'll see. Now, it's equipped with this dot product here, which allows to define a norm and a distance. The distance will be the norm of the difference between two vectors. And therefore, the dot product in the Euclidean space can be used to determine, spatial distances, or, of course, the amplitude of a vector. That could mean the intensity of what it represents, measure the influence of a force on another force. Now, what we have to remember is that the bigger the scalar product or the dot product is, and the smaller the distance between the vectors is. And that's very key, as we'll see in a few minutes. Now, Hilbert space is just a generalization of the Euclidean space, and that means the Euclidean space is an example of Hilbert space in this particular case. Now, a Hilbert space is an n-dimension vector space over a field, generally C, which is complex numbers, but not necessarily. And it is equipped with an inner product, which is an extension of the dot product. which allows to define norms, distances, and therefore the difference between elements, which are vectors. And when I talk about differences here, I really mean it in the broad sense, how much alike they are or how much not alike they are. Now that we know what a Hilbert space is and why it can be useful to model physical behaviors and characteristics, it's time to see how we can use it in quantum physics. What we're going to see is that Hilbert spaces will allow us to model quantum object states and combine them, and also use vector bases to define states and also to define the evolution of states based on other states. Now, the Hilbert space used in quantum mechanics is defined over the complex numbers field. It's called C. And that means that the inner product will be a complex number. And it will be defined like this. It will be the sum of the coefficients here of each state vector here. Except that, again, these are complex numbers. And the first coordinates here will be the complex conjugates. The reason for that is so that the norm of a vector still is a squared plus b squared, real and positive, just like the norm, that we already know with Euclidean space, for instance. And so it's compatible. It's kind of a superset of the Euclidean dot product. And from now on, we'll use that notation here for the inner product. Now, in quantum physics, although some states actually correspond to measured values of characteristics, they're called observables, in some states we can only measure the probability to find a measurement in a future state. And we express this probability as a combination of states, and it's just like a basis in a vector space. So, the nice thing about Hilbert spaces is that there are vector spaces, and therefore you can express all of their vectors using basis vectors, which means, it's a sum of coefficients here, which are called the coordinates, and which are complex numbers in our case, with the basis vectors here, and any vector in the Hilbert space will be able to be expressed as a sum like that. And the reason why we use complex coordinates, complex numbers, in other words, the reason why those Hilbert spaces are defined over a complex number field will be given in the next video. Now, the state contains all the information that can be known about the quantum object, for instance, a particle, at a given point in time. I'm talking about so-called pure states here. The question is, how can we link its state with the measurement of some observable? And that's what we want to do in the physical world. And we want the states in the mathematical world to be isomorphic, right? So the idea is that if we take all the possible values for a certain observable, for each value, the particle will be in a given state. And there happens to exist operators that can be applied to the state to give us that info. And these operators will be described in more details in the next video, but they basically look like this. You apply this operator to a given state, and it will be equal to a complex number times that state. And this complex number in our mathematical world will be isomorphic to the value that we will measure in the physical world. That's magic. And those particular operators that we'll see in the next video, and the eigenvectors of these operators happen to form an orthonormal basis. That means that if we use those operators like this, well, we will be able to determine here the values that will be measured, for that state. This means that the eigenvectors of those operators can be used as a basis in the Hilbert space to express any states, and that's very important, as we'll see. And the corresponding eigenvalues, the Vj here, happen to be real, so you can actually link them to the measurable values that you will see in the physical world. How great is that? Now, the coefficients will express how much the state is close to or like the corresponding basis state. Why? Because the inner product can be used to express the coefficients used in the chosen basis. It goes like this. Okay, so you take a state and you write it based on the basis vectors, and then you use the inner product here with one of the basis vector. And so what you get is this result here. But it's an orthonormal basis, so that means that the norm of each basis vector is 1. And when you look at the inner product of two basis vectors, it will be 0. And so that means that the pKs here will be equal to this inner product of each basis vector with the states you are developing here. And therefore, it will be equal, by definition, to this value here, this complex value here. So that means that the complex coefficients of the state vectors are equal to the inner product of the basis vectors with current state. And so the coefficients express how much the state is close to or alike the corresponding basis state. And we'll use that result in a coming video to finally explain some of the quantum physics mysteries we're trying to solve. It's fascinating. So let's remember that. So let's summarize, what we've learned about the Hilbert spaces and the way we're using them. So we've seen that the state of particle is isomorphic to a vector of a Hilbert space. And thanks to that structure, the states can be expressed with complex coefficients in a given basis. And the inner product can be used to derive, which means to calculate the coefficients used in the chosen basis. And we can use some specific linear operators to determine the possible values of measurements. Crazy. So let's see now what those special operators really are.